Differentiating a composite function. Our objective in this lesson is to differentiate a composite function and use the chain rule for multiple composite functions. Let's take a moment to explore. If y equals x to the fourth, then the derivative of y with respect to x equals 4x to the third, simply using our power rule. Multiply by the 4, subtract 1 from the 4 makes a 3. Easy enough. If u equals x to the fourth, similarly then, our derivative of u with respect to x is 4x to the third. If y equals u to the fourth, our derivative of y with respect to u is 4u cubed, because we're taking the derivative with respect to u being that independent variable. Well, what if y equals u to the fourth, and instead of dy du, we want the derivative of y with respect to x? But this is not a function of x. So first, we go through dy du, meaning we do dy du, but then to get dx in the denominator, but no du in the denominator, we multiply by du over dx. Notice why du divided by du will cancel out to leave us with dy divided by dx. This is called the chain rule. We've linked a chain in order to get to dy dx by saying dy dx equals dy du times du dx. Because this variable, x, does not match this variable in the original equation u, we require the chain rule. Dy du is 4u cubed, so we could also write this as 4u cubed times du dx. What if y equals sine of x to the fourth? This is similar to what we did here, but instead of just x to the fourth, this is a little bit more complicated. This is a composite function, a function inside another function. X to the fourth is the outside function. The inside function is sine of x. So we can simplify this problem a little bit by saying, let's let u equal sine of x, and then we don't have to write such a complicated function. We could write that y equals u to the fourth. Now, because we're using a different letter, and I still want dy dx, I have to use the chain rule. So remember, dy dx will be dy du, because we now have y as a function of u, and then times du dx. So similarly to what we did above, dy du means the derivative of y with respect to u, which is 4u cubed times du dx. Now, because we actually said what u equals, we can take this a bit further and say that instead of 4u cubed, we have 4 sine x cubed, because u is equivalent to sine x, and then instead of du dx, we can actually take the derivative of the u function, sine x, its derivative, cosine x, so times cosine x. That is using the chain rule. Now, I like to think of this kind of like eating an M&M candy. Think about eating an M&M candy. Those are really yummy. You have the shell on the outside, which gives you the pretty color, and then you have the chocolate on the inside. Well, M&Ms are pretty yummy, so you really want to savor the M&M candy, not just bite into it and eat it all at once. So I like to think of the chain rule like savoring an M&M candy. First, as you suck on the candy, you eat the outside shell, then you get to the chocolate inside. Taking the derivative is the eating part of it. So if we think of it like this, the outside shell of this function is the part that's surrounding the function that's to the fourth, like x to the fourth or u to the fourth. That part is our shell. Then you've got the chocolate inside. The chocolate inside of our function here is sine of x. That's our chocolate. So first, we eat the shell, meaning take the derivative of the outside. So that would be the 4 times whatever's inside cubed. That part is just eating the shell. Notice we did not touch the chocolate stayed the same. Then when we get to the chocolate, that's taking the derivative of that part. That's going to be this part, taking the derivative of the inside, cosine x. This part right here, that's our chocolate. Looking at chain rule like an M&M candy is kind of fun. Not necessary, but something fun to think about. Let's take note of exactly what the chain rule is. If a function g is differentiable at x and a function f is differentiable at g of x, then the composite function f of g is differentiable at x, and f of g prime of x equals f prime of g of x times g prime of x. Now it's important to remember there are two ways to write a composite function, f circle g or f of g of x. Remember what those mean. So thinking back to the M&M candy, notice what we have first. The outside function is our shell. That's the f. So notice f prime happens first. That part is eating the shell. We don't touch the chocolate. Then we have the inside function. That's the chocolate. See how we're doing now the derivative of the inside? And that part is eating our chocolate. We didn't touch it until we were done eating our shell, if we want to think of it like an M&M. Now, in Leibniz notation, if y equals f of u and u equals g of x, this is what we were looking at before. dy dx equals dy du times du dx. Again, we can think of it as y is the outside function, or the shell. So this part right here is eating the shell of our M&M candy. And then du dx is taking the derivative of the inside function. So that's like eating the chocolate part of our M&M candy, if you like to play with it like that. Examples. Find the derivative of each function. So here we have y equals the quantity x cubed plus 7 to the 10th. So I notice this is a composite function. There is an inside to this function. We're going to call that u. U is our chocolate. That is x cubed plus 7. That way I can write this simpler as y equals u to the 10th. Doesn't this look much simpler to take the derivative of than this guy right here? Sure does. So if I take the derivative of y with respect to u, that is 10u to the 9th. But ultimately, I want the derivative of the function, which in this case means because it's a function of y with respect to x, I want the derivative of y with respect to x, not the derivative of y with respect to u, since u is what I made up. So to get the derivative of y with respect to x, I'm going to do the derivative of y with respect to u times the derivative of u with respect to x. So what does that make? The derivative of y with respect to u, we wrote it as 10u to the 9th times the derivative of u with respect to x, which we didn't write yet. If u equals x cubed plus 7, then the derivative of u with respect to x is 3x squared. So du dx is 3x squared. Because u stands for x cubed plus 7, I'm going to finish that substitution. 10 times the quantity x cubed plus 7 to the ninth times 3x squared. This is an acceptable answer, but we can clean it up a bit. 3 can multiply to 10 to make 30. I can bring the x squared in the front times the quantity x cubed plus 7 to the ninth. Also an acceptable answer. Now notice if we're thinking of this like an M&M, the outside of the function is the power function where we have stuff to the 10th. So our first part of taking the derivative is this outer part where we do 10 stuff to the ninth. Then we eat that chocolate inside, which is the derivative of that inside, 3x squared. So all of these steps of writing out what u and what y are in terms of u can be helpful. Also, just thinking of it as doing the outside first and then the inside derivative can be helpful. You'll find a way that works best for you. Let's take the derivative of y equals e to the x squared minus 4. Now it's important to notice this is a composite function because your function that's easier than this would be if only x were in the exponent, such as if we wrote y equals e to the x, but I already use x differently, so I'm going to call it e to the u. That means our u is all of what's in that exponent. That's our inside function. U is x squared minus 4. In terms of what I wrote y is, dy du, is just e to the u. Remember, e is our easiest. But what I want is dy dx. So remember that dy dx is dy du times du dx. So dy du, e to the u, times du dx. The derivative of x squared minus 4 is 2x. And then I can substitute what u equals. So e to the x squared minus 4 times 2x, which is usually written with the 2x in front, so I don't need parentheses. 2x times e to the x squared minus 4. Both of these versions are a good derivative. Notice I'm not saying this one is a good derivative because this still has a u in it. Our original function did not have a u in it, so I'm not done until I get everything back in terms of x. Notice these two examples. For both of these, we want the derivative of the function. They look very similar, but they are not the same function. If we rewrite this with parentheses, this is the same as saying secant of x, function to the fifth, with the parentheses around the secant of x. Whereas this one is the same as saying the secant of the function x to the fifth. Pointing that out helps us to realize what the inside function is. What is the chocolate? What is the part that is inside function? In this problem, the u, the inside, the chocolate, is secant x. Whereas in this one, the inside function, the u, the chocolate, is x to the fifth. Those are very different than each other. If u is secant x, we know we're going to need du dx, so I'm going to do it now, secant x tangent x. And in this one, du dx, 5x to the fourth. Let's continue with just this first problem on the left. So if I say u is secant x, that simplifies what y is to be u to the fifth. So when I take the derivative, dy dx, that means I need dy du times du dx. dy du, the derivative of y with respect to u, 5u to the fourth. Du dx, the derivative of u with respect to x, secant x tangent x. And then, of course, we must plug what u is back in. So we've got 5 secant x to the fourth times secant x tangent x. An acceptable answer, of course, but it can be cleaned up. Secant x to the fourth, and another secant x makes secant x to the fifth. I'm going to write it without the parentheses. Secant to the fifth x, and then we just have a tangent of x. A much cleaner answer. Let's see how it's different on this one. If u is x to the fifth, this one looks like this. Y equals secant of u. So again, for dy dx, I still need dy du times du dx. Dy du being the derivative of y with respect to u. That's going to look like this. Secant u tangent u. And then times du dx, 5x to the fourth. I'm not finished because I still have u instead of x. U is x to the fifth, so let's see what that looks like. Secant x to the fifth times tangent x to the fifth times 5x to the fourth. I can clean this up a bit, although this is an acceptable answer. Usually we would put the polynomial in front of the trig function. So we've got 5x to the fourth, secant x to the fifth, tangent x to the fifth. Also an acceptable answer. Let's take the derivative of y equals 1 over 5x squared plus 6. This is a quotient. We could absolutely use the quotient rule. Or we could rewrite this and use the chain rule. If I rewrite this, I bring up that denominator to be 5x squared plus 6 to the negative first power. And now I don't need a quotient rule, I can use the chain rule. Notice I have an inside function right here. My chocolate is this. U is 5x squared plus 6. So I can write this y function simpler as y equals u to the negative 1. Well, I want the derivative of y with respect to x. That's the derivative of y with respect to u times the derivative of u with respect to x. What is the derivative of y with respect to u? What is the derivative of this? Negative 1 times u to the negative 2 times, what is the derivative of u with respect to x? The derivative of the inside function is 10x. I'm not finished because u isn't x, and my original function was all in terms of x. Now, I probably would do better rewriting this first, then plugging in the x, but either way is okay. So let's try without rewriting first. Negative 1, u is 5x squared plus 6 to the negative 2, and then times 10x. This is an acceptable answer, but I would want to clean it up a bit. Negative 1 times 10x, those stay in the numerator, negative 10x divided by this, because of the negative exponent, goes back down, 5x squared plus 6, but now the exponent is positive 2. A much cleaner answer. Let's take a look at this example. Suppose h equals f of g. Find h prime of 1, given that f of 1 equals 2, f prime of 1 equals 1, f prime of 2 equals negative 4, g of 1 equals 2, g prime of 1 equals negative 3, and g prime of 2 equals 5. They've given us a lot of information. Don't be distracted by the fact that just because they gave us all of this doesn't mean we have to use it all. Let's start with this, h equals f of g. Another way to think of that is h of x equals f of g of x. That's a composite function. So when I take the derivative, h prime of x, notice I don't jump straight to h prime of 1. First I take the derivative with respect to x. I'm going to do the outer function. The shell is f. So first I do f prime, where I leave the inside just as it is, g of x. The chocolate doesn't change. then the inside derivative, so times g prime of x. Eat the shell first, then eat the chocolate. Now I can plug in the value x equals 1, so h prime of 1 equals f prime of g of 1 times g prime of 1. Notice I didn't reference any of these values yet. Now I can go to those values. I need g of 1. G of 1 is the value 2, so 2 will go in that spot. I also need g prime of 1. G prime of 1 is negative 3. Negative 3 will go in that spot. Let's write what we have so far. F prime of 2 times negative 3. F prime of 2, I don't have that value yet. So I go to what I was given. Here's f prime of 2, negative 4. This right here, negative 4. So now I can simplify my work. Negative 4 times negative 3 is an acceptable answer, but of course it's cleaner as 12.